The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, let's get started. Today's topic would be distributed algorithms. We will look at two new algorithms, but they are similar to what you have seen in the lectures. So it will also be a review of some concepts in lectures. So our first example would be, again, leader election, the simplest example. But this time, the network topology would be a ring. So in the lectures, the example we see is a clique, meaning they are fully connected. Right? Every node can talk to every other node. There, if you remember, our solution is for everyone to generate a UID or a random number. And if you are the maximum, then you output you are the leader. You can do that because you are connected to everybody, so you immediately know what random number everybody generates, and you can compare whether you are the largest. Now, the idea is the same if we have a ring. So you want everyone to generate an ID or a random number. I'll just say ID from now on. And you want to collect everyone else's ID so that you know whether your ID is the largest among all of them. OK?
Where do you do make a comparison, like comparing the numbers?
Pardon?
Where is the comparison competition happening?
OK, the question is where the comparison happen?
Mm-hmm.
So we first need some way to pass the numbers around such that everyone has everyone else's number. Mm-hmm. Right? You have the number of everyone, then you can compare whether the largest equals yours. Okay? If the largest equals yours, then you know you are the largest, and you're going to output, I'm the leader. Okay, so the difficulty is just how to pass the numbers around so that everyone sees everyone else's number. Any ideas? Simple solution? Well, there's not much you can do. You just connect to your two neighbors, the left one and the right one. So how do you propagate the information? Go ahead.
You can take the maximum of your ID, neighbors' IDs, and kind of broadcast that.
OK, so what does broadcast mean here?
Like tell your neighbors what the largest of your value and your neighbor's values is.
OK. And yes, let me call them A, B, C, D, E, F. Then C can tell D or can tell B, but how does C tell E? So it would be just say everyone talks to its right neighbor, and then B has A's ID, C has B's ID, D has C's ID, and then continue, right, and pass around next time. So just to make it perfectly clear, say they generate some random IDs, that's 5, 10, 20. And then in the next round, A would send its ID to B, B would send its ID to C, C would send its ID to D. And in the next round, B would pass this information along to C, and C would pass the information to D, and just continue, and eventually everyone will have everyone else's ID. So how many rounds do we need? If there are n nodes in the system?
Are they probably in just one direction or two neighbors?
I think you can do it either way. Yeah. It will be, if you propagate both ways, it's probably 2x faster. Yeah, correct. It's just O of n. Right? But to keep it simple, let's say we just propagate in one direction. Right? That's also fine. It's still O of n. So how many messages are sent in total? Pardon? N squared. Yep. Is that obvious to everyone? Or can you give an explanation?
Yeah, at each round, everyone sends a message to its neighbors, right? So
Yeah. Yeah. No, every round, everyone sends a message. Or you can think of every message is propagated n times, and there are n messages in total. Okay. Yeah, that's definitely a solution. Well, you can imagine it's probably the naive solution. And can we do better than that?
In this case, are we assuming they know that there are n of them? Like, there's no termination.
Okay, good question. So if they know there are n of them, yep, then they know how to terminate. So your question is how to terminate, right? If they don't, eventually you will receive your own ID on the other side. If we keep sending left, eventually you will receive it on the left port. And yeah, that's an indication of termination.
Are we
Question.
assuming that the generated IDs are unique?
Yeah, we usually assume that, yeah. Either it's a unique user ID, UID, what does U stand for, by the way? Or if you generate random numbers in a large range, it's very unlikely that they collide. Okay, so can we do better than that? Have some idea?
Once something, probably some sort of binary search thing where you only pass it to the one that's bigger.
Okay, I think you have two ideas. And binary search, we'll see how that works later. So you said only forward something that's larger?
Yeah, like only forward to the larger.
Okay, yeah, that's on the right track. So one obvious thing we can do is that, so we actually don't care what all the IDs are, right? We only care whether a certain ID is the largest. So for example, in this case, when A sends its ID 5 to B, B knows this 5 won't be the leader, right? Because 5 is too small. It's even smaller than his ID. So B can choose to drop this message. Right? There's no point in passing that message further. Same thing for this message. C knows that 10 is too small, and it doesn't have to pass it along.
What are the IDs of this ID? Is it like the links and IDs?
The ID? It's just the integer each node chooses at random, say. Yeah, the only purpose of the ID is to break symmetry. So yeah, like we have seen in the lecture, if they don't do this, if they don't have any unique identifier, they won't be able to select the leader. And when they have a unique number, then they can select the largest one or smallest one or in some way. Okay, does this optimization make sense? We can drop several messages that have no chance of becoming the leader.
What is the upper bound of it? Is it still n squared?
Correct? Yep, that's very good question and very good answer, by the way. But how effective is this? Well, in the average case, we may be able to drop some messages, but there are pathological cases where it actually doesn't help at all. Say, this is the ID we choose. Then when this 20 is sent around, B cannot drop it, right? Because it may be the largest. And when this 10 is sent to C, C cannot drop it. And when 20 comes along, it also cannot drop it. Right? So no node can drop any message. So its worst case is still n squared. Okay, so let's think about the binary search equivalent, or how to binary search in this case.
So binary searching through what?
Yeah, good question. It's not very obvious binary search into what. Yeah, just some binary idea that will give us a n log n bound. So actually, this is the better algorithm. But once you have a log n, you can probably get. Okay, go ahead.
How about like kind of merging, like instead of finding the global maximum, finding like local maximum, then balancing out
Yeah, that's on the right track. Yeah.
like clusters of some points.
Yeah, that's definitely the right idea. Yeah, let's detail it a little bit. How do you carry it out?
Divide the set two parts, like two parts. Yeah. Like
Okay.
kind of divided complementary.
And okay, so then it's let them select their leader respectively and compare which one is larger. It's an interesting thought.
Like, for example, AB finds the maximum between these two, CD finds the maximum, EF maximum, then just kind of merging, considering them as a one node.
I think the first difficulty I see is that if you cut it by half, it's no longer a ring, right?
Also, they can't cut themselves in half. They can't act as
Yeah,
one
yeah,
body.
correct. Yeah, yeah. Yeah, it's definitely not an easy problem, not an easy algorithm. And the idea is to well, you had the right idea that we want to, what's the word? Let the weak candidates shut up early. Right? So what I mean by that is, say we have several rounds, so this B and A and C. We will let B only propagate to A and C first. If B is the local maximum among ABC, then B will try to talk further, increase its range. If B is not the local maximum of ABC, then yeah, it can be quiet. It doesn't need to send messages anymore. If B succeeds in the next round, then it will further increase its range to try to talk to more people. Okay, so how does it work in detail? Well, so in round I, we will let a node send this message up to 2 raised to I hops. In this case, it's 1, and in next round is 2, and then 4. If at any point some node, like along this range, decides that you are not the local maximum, then they will reply that yeah, you no longer need to send messages anymore. Right? If this message successfully reaches this endpoint, that 2 raised to I hops, then this guy will respond. And this guy, if it still thinks you are the local maximum, then it will respond the message, well, saying, yeah, continue. Okay. And if the sender receives this continue message on both sides, then it will continue into the next round. Otherwise, it will go inactive. Is the algorithm clear?
Then how do we choose the next maximum? Like next, the node which has to send the message?
Say that again?
Like after receiving don't send again. Like we have to choose one node which has to send.
Oh, okay. In the first round, everyone sent their messages. Okay. Then some of them will go inactive because they learn they are not the maximum, and the remaining, the surviving ones, will continue sending messages, and then half of them probably will die in the next round, and the surviving ones keep sending messages. Make sense?
How will it send messages to I? Like it can only communicate with its neighbor, right? Not the node that to I.
Yep. So we will send a message of this form, say, well, some message, and then we will send a hop and a direction, either left or right. And this hop will initially be set to 2 raised to I, the number of round. Then when this guy receives the message, it will decrement the hop count and pass it along. Right? And every node, when forwarding the message, will decrease that h by 1. And finally, when it reaches here, that number becomes 0. And when you see when a node sees a message with 0 hop count, it's going to reverse it, send it in the other direction, and again set it back to 2 raised to I. This message, I should say, ID. And at certain point, a certain node may decide this ID is too small, it doesn't have a chance, then it can directly send it in the opposite direction, replying a message saying, you are too small. Okay, so any more questions on the algorithm itself? If not, what's the next step? Yeah, time complexity. Oh, I already claim it's n log n. Is it? Sorry. This is round. This is message. This is also message complexity. Okay, so why is it n log n?
The login layers, yeah, like
So we have a certain number of rounds. So how many rounds do we have?
2.
Yeah, maybe, but yeah, I'll just say log n. Okay. Because yeah, you are increasing your hop length. And we're going to compute like how many nodes are still active in each round and how many messages are sent in that round. So, well, the number of nodes active will just be this number if we start from 0. Why? Because the first time everyone is active. In the next time, only 1/3 of them will be active, but we said we are conservative here and we put 1/2. Right? Next round is actually 1/5, because the local maximum, if it's local maximum, it means like these two and those two will go inactive. But we put this as a upper bound. So this is the number of nodes that are still active. And they will send the message up to this many hops. Okay. And there are 2 directions. And you send the message back, and then, send the message forward, and someone will reply. But in the end, this is n log n. Yeah, I think I got 8 n log n. So my recitation note says it's 4 log n. I'm not entirely sure what's going on. Yeah, but you can double check whether this is correct or the recitation note is correct. I is the number of round in the ith round. Yeah, this many nodes are still active, and each of them will send the message this many hops. And I didn't mention whether the network is synchronous or asynchronous, and it turns out it doesn't care. This algorithm can work for both synchronous and asynchronous. Apparently, it works for synchronous networks. If it's asynchronous, then what changes is that different nodes are in different rounds. Right? A certain node may be far ahead than the others, but it's fine. Eventually, they will converge to the correct result. Okay, so let's look at the second problem. problems is defined even simpler. We just want to count how many nodes are out there. We want the algorithm to work both synchronously and asynchronously. By that, I just mean we have a network. Well, say you have a lot of nodes after that. Just want to count how many nodes are there in this network. So I'll give you, say, 1 minute to let's first come up with a high-level plan. Oh, is the problem clear?
In the worst case, always good.
Mm-hmm.
The worst case.
OK, I haven't defined that. Let's not worry about complexity now for now. The complexity will depend on the number of nodes n and the number of edges e. Yeah. Let's just get it functionally correct. Can anyone share a high-level strategy? Go ahead.
So each node will store the IDs of the other devices it has received. So basically, it's gonna propagate the sets of the nodes, its nodes.
Mm-hmm. On what edge?
For this one.
Yeah, it was sent on both edges.
Itself first.
Mm-hmm. OK, so then maybe it send the 1 here and send the 1 here, there. Then this node will think it has a child, right? Which is this one. Let's just say this is the entire network. And what message does it send to this guy?
Reinforce it.
Mm-hmm. Right, you probably need send 2 here because you have 1 and this is possibly its child, right? But then we're double counting this node. You see the problem?
Do nodes have their IDs, like unique IDs?
Oh yeah, they have their IDs.
We can send the IDs instead of the IDs
Oh,
to the network.
OK. We're going to send all the IDs.
Yeah, neighbors. And after
Okay.
n steps, it's gonna have all.
OK, yeah, that's an interesting thought. And then you may still need a root, and that one will have everyone's ID, and then see how many unique guys are there. Okay, interesting. Does this algorithm work? Yeah, I don't see any problem. Okay, but let me still repeat what our algorithm is. It's because it's closer to what's in the lecture. So we're going to find the spanning tree of this network. Right? A spanning tree means, well, like I have to cut one of these edges. Okay. If I have a tree, then I can have every child report to its parent, like how many offsprings, including myself, do I have. Right? And this node will sum up all its children and report to its parent. Does everyone get that? So first, we'll find the spanning tree. And second, we'll have child reports to parent.
How can we find this spanning tree?
Good question. So in the lecture, we have seen an algorithm that finds BFS spanning tree. For synchronous networks. Okay, this is review of the lecture. How does it work? Each node will say we need to first choose a root. And our root will just send a message to its neighbor, and yeah, saying you are my child, you are my child, you are my child, you are my child. And then every node, upon receiving this message from the parent, will search among its neighbors. Right. So the neighbors that haven't got a parent will acknowledge this sender as the parent. Okay, that's a little messy. So this node will search to the leaf node, but then it will also try to search for this guy. But this guy already has a parent. Then yeah, it will say, yeah, I already got a parent, and blah, blah, blah. This will give us a BFS spanning tree. What does it mean? It's a spanning tree found by BFS. Does it work for asynchronous network? Go ahead.
This version doesn't, but there's a different version that uses kind of an edge relaxation technique.
Yeah, correct. And so why does this version not work for a synchronous network?
Because different nodes can be on a different round number, so that a longer path could end up going to a node.
Yeah, exactly. So let me give a concrete example. What does asynchronous network mean is that, well, messages travel at different speed. Say this link, for some reason, is temporarily down. Right? And this node doesn't receive the message from the root. And then this message travels very fast. And this message also travels very fast. So this message may reach this node earlier. And then this node will think of it as a child of this node. Okay? And then this message comes along finally, but this node says, yeah, I already have a parent, and I'm going to reject you.
So it still makes a spanning tree.
Yes, good point. This is not a BFS spanning tree, but it's it's still a spanning tree, right? So in our problem, we are totally fine with it. Yeah, but you do have to know if you really want a BFS spanning tree in an asynchronous network, then you have to like record the distance and do the relaxation and so on and so forth. Okay, so we'll just use this algorithm, the BFS spanning tree algorithm. Just run it asynchronously. It doesn't find the BFS spanning tree, but it finds a sum spanning tree. Okay, how does this algorithm work? We will have several variables. The first one is parent. We will initialize it to this undefined symbol. Okay. Then every node will pass around this search message. I'll use a slightly shorthand notation than from the lecture. Okay, let's say the code I wrote is for process U. Okay. If we receive a message, a search message from V to U, that means V is trying to become our parent. Okay. And if I do not have a parent yet, I should set the parent to V. Okay, so what's the next step? We got this search message from our parent, and we have to pass it along.
Should we send them to the like add your child to the video?
Oh yeah, great. Yeah, we first need to respond by saying, okay, I'll use a shorter notation. Send V is a queue. That's the message that will be sent to V at some point. Well, the message we sent is parent 1, parent true. This is a response to V saying, yeah, you are my parent. Okay, then else, we also have to respond. By saying parent 0. You are not my parent, because I already got some other parent. Okay. I'm missing a step here. If we receive a search message, go ahead.
Send messages to all the other nodes.
Yeah, we need to pass it to all my potential children. So I'll use this gamma U, meaning the neighbors of U. Right? And then I'll send them a message. What message? Search. Okay. Okay, so well, naturally, since we have a search message and we know how to deal with it, now we are sending this parent message, we'd better deal with it, right? So then the next chunk of code should be, if we receive this parent message, I'll say parent B, meaning this message comes with either true or false. Oh, I received this message from some node W. Right, okay, I'm still U here, because I just send all the message to all the Ws, to all my neighbors, and they should give me a response. Okay, if B is 1, that means this particular W take me as its parent. Make sense? Okay, so I'd better have a list of my children. I want to track that. I want to keep track of that. How? We will create a new variable called children. It's going to be initialized to what? Yeah, empty set. And now if this B is 1, then I'm going to put W in this children list. Okay, I'm leaving some space here, because our route should be slightly different. So every other node will send search messages when it receives the search message. We need someone to initiate. Make sense? So if U equals root, we say the root is V0. So two things should happen. First, we should set its parent to some special value. Let me just say root. And then I should copy this blob of code to here. Okay. This is a little crowded, but I hope it's still legible. Okay, this is already almost the correct algorithm, except that we don't know how to terminate. Right? If we wait long enough, then everyone will receive all the responses, and everyone will know its parent and its child list. But how do we terminate?
After n rounds.
Yeah, that's one way to do it, after n rounds. But the whole point is we are trying to find what n is. We don't know how many nodes are there.
If we receive rejects for all requests that all research,
Say again?
if for all the search, if we receive a reject.
Oh, yeah. If you receive a response, either parent 0 or parent 1, from all your neighbors, then your job is pretty much done. Right? But the others have not. Right? So you send the message very fast, they responded to you, and they are still working very hard. Okay? So then we need to use the technique from the lecture that's called converge cast. So everyone will send a done signal when it is done, and all its children are also done. Okay. To do that, I'm going to define a new variable called searched. Searched means someone has responded. Okay. In this case, W has responded. I'll put it into the searched list, no matter whether it accepts me as parent or reject. Okay, then naturally I need to define this variable here. Okay. As a last step, if this searched list equals my neighbor list, that means everyone has responded, and all my children are done. Then I need a new variable called done. That's another list tracking who has finished and who has not.
So
Okay.
What was the first one?
Say again?
What was the first one?
This one? Searched means someone has responded to the search message. Okay. Done means all its children are done. Okay. It's I haven't write how done is defined. Give me a minute. In this case, I'm going to send my parent a message. This is the step of converge cast. What do I send? I'm going to send I'm done. Okay. Then whenever we create a message, well, we should deal with that message. If we receive a message, I'm done, what do we do? Okay, from W. Then we're going to mark that node as done. Okay, there's a subtle point. So someone has to initiate the done signal. That's going to be our leaves. Why? Because when this condition check, they don't have any children. Their children list is empty set, and their done list is also empty set. So they're going to send the I'm done signal first. And then all the intermediate nodes will send the done signal when all its children are done. Right? Okay, so this is the converge cast version. Only gives us a termination point of our spanning tree search. Right, we haven't counted the number of nodes in the network. But that's a small modification. We're just going to include that number in the I'm done signal. So then I need to define another variable called total that's initialized to 0. This variable will track how many nodes do I have in my subtree, including me and all my children. Then when I send the I'm done signal, I'm going to send this. Sorry, that's not the right way. When I'm sending the I'm done signal, I'm going to send my total number of offspring with it. Right? And when I receive someone, one of my children reports that I do have T children, I need to increment my total by that amount. Okay, I made a mistake again. Should be total plus 1. Right? Because I'm counting all my children, and then I should include myself. So that's the complete algorithm. Yeah, one purpose is just to create a different angle to look at distributed algorithm. We usually just draw the network graphs, but sometimes it's helpful to think about how the code actually works. That's all for today.